Good morning, students. In this video we will discuss a few sums involving Dirichlet characters. So in this section we will deal with the principal Dirichlet character chi modulo k. But in fact the proof of this theorem, this is also valid for any arithmetical function which is periodic with period k, and this theorem will be useful in the proof of Dirichlet theorem, which is in the next chapter. So let us start this theorem. The theorem says if chi is a non-principal Dirichlet character modulo k, if chi is a non-principal Dirichlet character modulo k, and f is a non-negative function which has a continuous negative derivative, for all x greater than or equals to some fixed x naught. Then for any y greater than or equals to x and x greater than or equals to x naught, we have this summation chi n f n is for all n greater than x and less than or equals to y. This is just order of fx. Secondly, we have to prove if fx tends to 0 as x tends to infinity, then this infinite summation chi n fn for all n varying from 1 to infinity, this is convergent series. And thirdly, we have to prove for all x greater than or equals to x naught, this summation chi n fn for all n less than or equals to x, this is infinite sum plus order of fx. So firstly we prove this first condition. Let us define capital A to be the partial sum of chi n for overall n less than or equals to x. Now since we know chi is non-principal character, so ak, which is actually sum of first k entries of chi n, because ak, this is summation of chi n for all n less than or equals to k, which means n is varying up to k. Now this is sum of the k entries of the function chi, and this is non-principal character, and we know sum of first k entries, that is 0, because we know in the table of Dirichlet characters, sum of k entries in any row except the row corresponding to principal character, that is 0. So because this is periodic function, chi is periodic function, so we know a of n k, this is 0 for all n up to infinity also. So let us take mod of ax. Now ax is summation of chi n, so mod of ax is less than or equals to summation of mod chi n over n less than or equals to x. Now we know mod of chi n, that is either 0 or 1, because for the integers which are co-prime to k, for the integers n which are co-prime to k, this is just a root of unity, and for the integers which are not co-prime to k, this is 0. So it means this summation, this is less than 5k, because we know there are only 5k integers which are not co-prime to k, and by periodicity a and k is 0. So that's why mod of ax is less than phi k for all x. So if mod of this is less than phi k, and phi k is fixed quantity, so we can write here ax as just order of 1. Now we will use Abel's identity to prove the equation 1. So let us start from summation chi n fn over n lies between x and y. So by Abel's identity it will be fy ay minus fx ax minus the integral at f dash t from x to y. Now since we know ay is just order of 1, so this quantity is order of fy. Similarly the next is order of fx, and the last one, because this is integral of something, so this is integral of order of 1 f dash t, so we can write it as integral of minus f dash t, order of integral we can write it. So all the values here are order of fy, order of fx, and when we solve this integral it will also become order of fy plus order of fx. So the terms here are just order of fy, order of fx. Now we know fx is a function which has a negative derivative. So if fx has negative derivative, that means fx is decreasing function, and since y is greater than x, so fy is less than equal to fx because it is increasing function. So both the terms order of fy plus order of fx can be included in just one term, order of fx. So this proves our equation 1. Now for the second part, if fx tends to 0 as x tends to infinity, then from equation 1, since this partial sum, this is just order of fx and fx tends to 0, so it means right side of this equation 1, this tends to 0. So by Cauchy's convergence criteria, summation chi n fn from 1 to infinity, this is also convergent. Now for the last part, we start with summation chi n fn from 1 to infinity, and we can split this summation into two summations. One is over n less than equals to x, and other is n greater than x. And we write the second summation n greater than x as n less than equals to y and limit y tends to infinity. From the second part, this summation is convergent. From the second part, this summation is convergent by Cauchy's criteria, and from first part, this summation is order of fx. So the second part of this just becomes limit y tends to infinity, order of fx. Now order of fx is independent of y, so that can be written just as summation chi n fn for n less than equals to x plus order of fx. Now because the second term is just order term, so we can interchange the positions of this summation and this summation. So the third part is also proved. Now we apply this theorem to find some results which we will use later. We will apply this theorem to the functions fx is equal to 1 by x, and similarly fx is equal to log x upon x, and later on we will apply fx upon 1 upon root x for all x greater than equals to 1, and we will obtain this theorem when we put fx is equal to 1 by x or log x by x or 1 by root x. So we find out this summation chi n upon n from the third part of the theorem, chi n by n plus order of 1 by x. So this is our equation. Let us say a chi n log n by n, again for n less than equals to x. Let us say this is b. Now let us say this is equation C. We will use these equations A, B, C later.